We're going to use technology, which means graphing calculators, right? How could we do this? We've talked about the way you can use the tables, and that's fine. That's a good way. I'm going to show you another way that I actually prefer. I don't think I've showed this to you. So one way you can do this is we're approaching -8, right? So for the limit to exist, and we're going to emphasize this again today, what would have to happen? What does that mean? For the limit to exist as the ant crawls towards fill in the blank. Okay, as the ant crawls towards an x value of -8, well, he doesn't necessarily have to be able to make it to -8. I mean, it may not even, the function may not, it's not defined at -8, right? But,
It's defined up to -8.
So-
Doesn't stop like -4.
okay, and this one actually stops at -6. But that's okay, because -6 is not -8. As long as there's some set of values surrounding -8 where the function is defined, and there is, right? It's the domain excludes -14 and -6 and -8. Everybody agree? Because those are all actually not -6. I don't know why I said that. -14, right? Because there's a denominator that has an x in it. If x is -14, would everybody agree that that fraction right there is going to go to 1/0? Can't do that, right? So 14 has to be excluded from the domain. So does obviously -8, right? But as long as there is some set of values, as long as there's some neighborhood we can define that surrounds -8 where the function is defined, clearly that's the case, right? How big does it have to be? Arbitrary. But it's got to include an infinite number of points, right? But as long as, infinite number of points can fit in any interval regardless of how small, right? The ant has to be able to take an infinite number of infinitely small steps towards -8 from both sides, though. That's my point, right? Remember what we said, the ants that approach -8, the limit just means the y value they anticipate stepping on when they get to -8, right? Whether or not they get there is irrelevant, right? The limit doesn't care if they actually get there. The limit just cares about where they think they're going to step. But for that limit to make sense, ants approaching from both directions would have to agree on where they anticipated stepping, right? Would you agree? Okay, so how can we check that? So let's plug in this expression using x's. So I'm going to make this look good. I'm going to pull down my fraction template. Oops, that's not what I did. And then I've got a fraction within a fraction on the top. Minus so far so good? Everybody agree? That looks like that. Okay, then let's define some values of x that are very close to 8. So or -8. Let's start. Don't ignore that number right there. That doesn't mean anything. Okay. But now I'm going to pick a value of x very close to -8. I'm going to pick one to the left, like -8.00000001. Okay? And I'm going to store that as x. So I'm going to enter that value. I'm going to hit STO for store, STO, x, enter. So that's my x value. If I go up and grab that original expression and hit enter, why is that significant? What is that? Yeah, we just evaluated the function at that value of x that's very close to -8. Okay, so that appears to be the limit. Now, if I want to know if that's changing, well, I could just go back and pick values. Like, what if I pick a value like negative? This is where the table is kind of useful. I won't even do it. Okay, I'm going to pick a new value. Now I'm going to pick one on the other side. Negative 7.999999, right? Now I'm going to store that. Oops, I got to store it as x though. Got to do that. Store it as x. And I'll go up and grab that expression again. And I'll evaluate it. What do you notice? Here's the value when I plugged in something to the left of -8. Here's something just to the right of -8. We're asked to write our decimal rounded to 2 decimal places. Can we safely assume that the limit is -0.28? Everybody agree? Because look, out to, like 6 or 7 places, we're getting the same answer on both sides. Everybody agree?
But we can't do that on the calculus, can we?
You can. You can do it on certain parts. I mean, there's going to be parts, you're going to have your graphing calculator for parts, and you're not going to have it for parts.
Okay, but once you have your graphing calculator, they're expecting you to use it.
Absolutely. If you have your graphing calculator, you're expected to use it to the best of your abilities. Absolutely.
Okay, so we're expected to say every management together.
Yeah. Yeah, so on the multiple choice questions where you have a graphing calculator, you would be stupid not to use it because all you're being graded on is your answer. Yeah, they're assuming you're going to use, you're going to be smart about taking the test. Yeah. If it's on an open-ended part and they say something like, if you're supposed to show your work and it says don't use a calculator, well, if it's a part where you have access to the calculator, yeah, you could check it, but they pretty much won't do that actually. If it's one of the couple questions on the open-ended where you have access to the calculator, they'll let you use it. And so you could say, yeah, I mean, you'd have to explain yourself a little bit, and we'll practice that. I mean, we're going to go through lots and lots and lots of open-ended questions this year where we'll get practice. But you would want to use the technology. I mean, those kinds of questions, typically they're really good questions, and typically they're just getting at something that's beyond just taking the limit. They want you to use the limit to do something important, okay? All right, just wanted to do a quick reminder of that. So for today, so close everything up. I need your undivided attention here. We're going to take a look at one-sided limits. All right, so quick review of some stuff we already talked about. We already looked at one-sided limits graphically and numerically. Okay, so all a one-sided limit means, like if we take this first example, will you guys tell me? If I take this example right here where I'm graphing g of x, here's g of x. If I take the limit as x approaches 2, the answer is DNE, does not exist. How come?
Depends on which side you approach it from.
Yeah, because that's one of those, remember clear back, this seems like an eternity ago, but about 3 weeks ago, we talked about the 3 places where limits don't exist. What were they? Okay, so different behavior on both sides. Asymptotes, or that weird oscillating one. And there are others too, but those are the only 3 we're going to look at in a class like this. If you go pretty far before you start talking about like Dirichlet functions or something where you've got these weird things that are doing bizarre behavior that's where limits don't exist. For us, we're not really talking about that kind of thing this year. Okay, but I could, if I wanted to, I could define a way that I could talk about limits. Because if we look at the graph of this thing, we can say more than does not exist. There's some interesting stuff going on there, and does not exist doesn't give us very much information. If an ant were to approach positive 2 from the left, the ant would anticipate stepping on a y value of -1, clearly from the graph. If an ant approached positive 2 from the right, he would anticipate stepping on positive 1. Good. And so we can articulate that in calculus by using one-sided limits. And we talked about this. This is all review. The limit of the function as x approaches 2 minus, what's the minus mean? Yeah, from the negative direction, which is the left. That answer was -1. The limit of g of x as x approaches 2 from the right is +1. Okay. And we actually, I think, brought those. Well, here's kind of the technical definition. You guys can. I'll put this in the notes. You can look at this if you want. But this is formalizing what we're talking about almost unnecessarily, right? everything we need to know conceptually we just got. But where this is important is here, right? And this is, I think, where we sort of left off with one-sided limits. We were able to improve our informal definition of a limit and call a regular limit now a two-sided limit. Right? Instead of saying when ants anticipate stepping on the same place, we can now say, well, okay, formally that means that the limit of f of x as x approaches L exists if and only if the one-sided limit of f of x from the left exists and the one-sided limit of f of x from the right exists and they're equal. Okay. And that just formalizes that notion that the ants have to anticipate stepping on the same place. Right? Okay. This is actually, we looked at a couple problems. This is just our notes from pre-roundup stuff when we were talking about this. So we did a little review of what piecewise functions, of the notation for piecewise functions and how we interpret those. And we looked at something like this, which is pretty simple. This just means, remember, that f of x is defined as a green piece and a purple piece, depending on where the ant is, depending on which part of the domain you're in, right? So if we wanted to take this limit, the limit of this piecewise function as x approaches 2 from the left, that's important. As we approach 2 from the left, which part of the domain are we in? The top one, isn't it? Right? The green one. Because the green piece is the one that's defined for values of x less than 2, right? So when we evaluate this limit directly, we would be plugging in the top function. Well, and the fact that we're plugging in 2 from the left, do we really need that negative sign there? No, we don't. We're just plugging in 2, right? That's the value we're approaching. But the direction is important here because it prescribes green versus purple function, the behavior, right? If we take the one-sided limit from the right, on the other hand, now we're standing on the purple domain, and so we'd have to evaluate f of x using x squared minus 4. Okay, no big deal. And in this case, we get two different answers. So you tell me, does the two-sided limit, the regular limit of f of x as x approaches 2 exist? No, because we have differing behavior in the left and the right. Okay? And we looked at something like this, right? And this was a good one because it gave us some good review of something that's really important. Yes, sir.
This is slightly unusual, but is it possible for our calculators to graph this one?
It is. It is possible, and I don't quite know. Actually, I know how on mine, but I don't know if I know how on yours.
On mine and use that.
Well, so we do probably want to tackle that at some point. I don't know if we'll have time today or not. If we don't today, we'll hit it tomorrow. Okay, how we can do that with technology. There are some ways around it, even if you don't know how, there's some ways to do it that are, I mean, you could just literally graph the two pieces separately as one, one would be y1, one is y2. And then you're just going to evaluate the piece that exists on a certain domain. You just choose y1 or y2 to do the stuff on the calculator. There's a better way, and I'll make sure I show you. I think we need to update all your, didn't we decide that you needed the new system to be able to use the new? Okay, so we got to do that at some point. Someday, maybe we'll take like half period in class and we'll get that done. We might have to go to computer lab to do it or something. Remember to bring as many, how about if we do it this Friday? Let's just say we're going to do it this Friday. Remember on Friday, if you can, to bring as many of those little USB cables, the ones that have a regular USB on one side and a mini USB on the other. A few people remember that. I've got a couple other ones where we can just trade the stuff back and forth, but we'll try to do some updates. And I've got some other programs I want to give you as well. I don't know if Friday's a good day for that or not. No. Friday will at least get your, remember that, Friday will at least try to get your systems updated, your operating systems on your calculator. Okay, so what about this? So here we've got this function, we're taking f of x to be x, the absolute value of x squared minus 4 over x minus 2. And we're going to approach that from the left and the right. absolute values make things difficult. Now, here's the thing you gotta remember about absolute values. You can't do regular algebra with an absolute value function, right? The best way to deal with absolute value functions all through the year is gonna always be to write them when you're doing calculus on them. Is always gonna be to write them as piecewise functions, okay? So how do we do that? Well, the definition of absolute value of A, as we said, absolute value of A equals just plain old A when the domain's positive, right? When the argument's positive. If what we're putting in the absolute value function is positive, the absolute value doesn't do anything, just leaves it alone. If the argument of the absolute value is negative, we have to make it positive, okay, by changing the sign, multiplying by -1, right? So for us, that meant absolute value of x squared minus 4. So what does that look like? Well, the absolute value of x squared minus 4 would be x squared minus 4 whenever x squared minus 4 is positive, and it would be the opposite whenever x squared minus 4 is negative. And here's where we need, I think, a little more review maybe, is how do we solve that inequality? That's not just a linear inequality, that's a quadratic inequality. So how do we deal with that? The absolute value of x squared minus 4 is greater than 0, for example. Well, we can do it a couple ways. And I briefly showed you one way, and I kind of thought maybe we got shorted on that just a little bit, so I want to talk about that. Yeah, okay, there's the stuff. Right, I did put it in there. So one way would be to say, if I've got the absolute value of x squared minus 4, I could just try to isolate x. And that's okay to do. You can solve for x. You told me the steps to solve for x would be to add 4 to the other side and then square root both sides, right? But remember that when we square root both sides of an equation, that means normally we'd have to include a plus or minus, right? How come? And I want to review this. This is important stuff. I know I went through this with you in Algebra 2, but it's been a while. There's some invisible steps there, so you can remember what those are. Like if we have something like, let's say, 2x squared minus 3 equals 5. What are the steps to solve for x? Add 3. Square root. Okay, you guys know that if I square root both sides, whoops, what's that going to give me? We got to include the plus or minus. Okay, and that's fine. You can skip the intermediate steps, but they're there for a reason, and understanding what they are becomes important now. So what are they? If I square root both sides, I get the square root of x squared equals positive 4. But what is the square root of x squared? No. It's absolute value of x. That's the mathematical definition of an absolute value function is it's the square root of x squared, right? So that becomes the absolute value of x equals square root equals positive 2. And what's our rule for that? If an absolute value of something equals the number a, then what's that tell us? What has to be true? What's inside, either what's inside, which is in the bubble, we'll fill it in later, is equal to what? A, could be A, or whatever's inside could equal negative A, right? Well, in this case, it's an x, and that's a 2, right? So that gives us either x equals 2 or x equals negative 2, right? That's just an or symbol, right? So just okay? Make sense? What's the rule for, similar rule for inequalities? What if we had something like the absolute value of, call it z, is greater than a? What's that mean? And a numerical example would be absolute value of x minus 3 is greater than 5. But what's this going to tell us? What do we trade that for? What would have to be true?
Z must be greater than A or must be less than negative
Must be less than 8. Does that make sense? Because the size of the number has to be big, but it could be positive or negative. That's really all that's saying, isn't it? Absolute value is telling us what's the size of the number, regardless of sign. Right? If it's positive, we just know that Z is big, right? It has to be bigger than A. What if it's negative? Then it's got to be big in the negative direction, right? Which means its value is going to be, signed value is going to be less than negative A. So those are the two things that would have to happen. So up here we would just say in this case, either x minus 3 is greater than 5, I'll write or x minus 3 is less than negative 5, and I'll just solve each of those independently. Right? Let's just go through this exercise, folks. I want to draw your attention to a relationship here that you probably haven't talked about a lot since maybe Algebra 2, I don't know, early Algebra 2. If we solve this, we get the answer x is greater than 8, or x is less than, what, negative 2? Okay, let's graph this. So here's positive 8, here's negative 2. Everybody agree? Where's the center of that distribution? What do you know? The center is at 5. What's the width of the distribution from the center? Oh, hold on. I don't think that's right. It's not 5. What is it? Yeah, we got this backwards. Right, the width of the center of the distribution is at 3, and the width of the distribution is 5, right? See those numbers anywhere? Right. What is an absolute value? It just means a distance from a, right? A distance from a point. So all this is saying, essentially, here's a way to think about this. Without even doing any of this stuff, we could look up here and say, okay, this is going to give us, we're seeking all values of x where the distance between x and 3 is greater than 5. Everything to the left of negative 2, everything to the right of 8, right? Okay. What would we get then if we did something like this? What if we said absolute value of z is less than a? Now we're wanting distances that are smaller, right, than some value. And so if I were to graph, like if I were to change this sign up here to a less than instead, what would that have done to my graph down here? Yeah, I just would have done that, wouldn't I? Right? Okay, and so what's the result then? This tells me that z has to be what? It's got to be less than a. Yeah, now we want values that are small, unsigned values that are small, right? So either they're going to be less than a, or on the negative side, they're going to have to be the right of negative a, meaning greater than negative a. Okay? Why do I bring all that stuff up? Well, one reason would be then when we get down to this point right here, that gets us to that point pretty quickly, right? That's how we remember to do that. Okay, because we've got this relationship here. We've got an absolute value relationship, an absolute value inequality, so we can always make that kind of a trade. And the value of that is we get rid of the absolute value nature and we trade it for a compound inequality. We get regular inequalities out of it. Okay? So that's one way we could get our domains. So the purple domain, we said then would be x is greater than 2 or x is less than negative 2. The orange domain would have been absolute value of x squared minus 4 is less than 0, we would have solved it the same way and gotten the absolute value of x is less than 2, so we get the and inequality, right? The conjunctive inequality. And then in the middle, obviously the places, where's that going to be true? Well, x is plus or minus 2. Those are the boundaries between the two. Those are the places where this is equal to 0. Okay, make sense? Okay, so we're able to trade, let me rewrite this whole thing to get kind of messy. So we're able to say, I say absolute value of x squared minus 4, we can trade for all this stuff. Okay, but that's not the function. The function is actually absolute value of x squared minus 4 divided by x minus 2, right? Okay, so could we rewrite this whole function as a piecewise function? Sure we could. Right? So let's summarize. We said this. Right? So that x squared minus 4 is greater than 0, and that's true. The absolute value of hand is negative hand. When hand is negative, x squared minus 4 is less than 0 when x is pinched between negative 2 and positive 2. And then in the middle, it's equal to 0 when x equals plus or minus 2. Right? But we were trying to find f of x equals the absolute value of x squared minus 4 over, was it x minus 2?
Yes.
How does that change things? Just dividing everything by x minus 2, aren't it? All right. So we've still got this, we've still got this piecewise function, but each piece is just going to get divided by x minus 2. So what's the top one going to be? I'm going to end up with x squared minus 4 over x minus 2, which is what? And then technically it's x plus 2 times x minus 2 over x minus 2, right? But those parts would cancel, and that's going to be in the domain when x is greater than 2 or x is less than negative 2. So that's all we're left with. It's going to be a line there, isn't it? The line x plus 2. Okay, what about the bottom? Well, aren't we just going to get, aren't I just going to get negative times that, right? So negative x plus 2 times x minus 2 over x minus 2, so those cancel. So I just end up with negative x plus 2, quantity x plus 2. And I'm between 2 and 2, negative 2 and 2. Okay. And then we already know in the middle, I guess I should include that, it's 0 and x equals plus or minus 2. So what's our limit going to be then? Our left-handed limit. We approach 2 from the left. Which domain am I on here, top or bottom? No, we were doing, let me make sure that's the question we were answering. Positive 2. Yeah, whoops, positive 2. Yeah. Oh, I did do positive 2. Bottom? I don't think so. Oh, no, you're right. It is. Yeah, it is. Because we're approaching positive 2 from values less, like 1.99. Right. Yeah, so we are the bottom. So this is green. So what's our answer going to be? Negative 4, right? Yeah, I'm just plugging 2 in for x, so I'm going to get negative 2 plus 2. Okay? How about the other one then? What if we're going to do the limit from the right? So that'd be the top one. Good. So we just end up with the limit of x plus 2 as x approaches 2 from the right, but who cares? 2 plus 2 is 4. Right? Okay. That looks like a lot of stuff because we did a lot of review, but if you think about that, what's our strategy? Because this is the kind of question you're going to see on like the open-ended, I would say you're highly likely on the AP test, stuff like this. All we had to do was take this function, and our goal was to write that as a piecewise function so we could take the limits from the left and the right. With a piecewise function, it's easy, right? All we had to do with the piecewise function is decide which part of the domain were we on in our piecewise function. Okay? So there is one other way to do this. And there's just a quick reminder about the stuff we talked about, a reminder about solving absolute value inequalities. There is one other way to do this, though. We could say, if we want to solve the equation, solve this, right? X squared minus 4 is greater than 0. Okay. This is kind of cool. Yeah, I don't know if you've seen this before or not, but I like this. We want to know, where is that expression positive value? Okay, one way we could do this is we could factor x squared minus 4. X squared minus 4 factors into, good, x plus 2, x minus 2, right? And let's just look at the behavior of those two factors independently. And there's a way you can sort of graphically represent this. It's kind of useful. So if we take x plus 2, and let's just look on a number line, where's the 0 of x plus 2? Negative 2. So at negative 2, we're going to get a hole. And then if we were to look at all the places where that's positive valued, wouldn't that be up here? Right? It's going to be negative value to this expression would be negative value to the left of negative 2. Okay? What about x minus 2? Where's its 0? 2. Everything to the right, would you agree, would be positive value? Okay. To the left would be negative value. Okay, so now let's look at the product of the two. Okay, well, where this is equal to 0, 0 times something else is 0, right? So would you agree that we're going to have a hole right there, or there's going to be a 0 right there, right, of that function? How about right here? Well, we have a 0 of the red function, so we're going to have a 0 there also, which it doesn't have a value, does it? It's 0, either positive or negative. Where is it going to be positive? Think about where we're doing a product here, right? So we're just following the rules for products, sign rules for products. So would you agree that where the green factor is positive and the red factor is positive, the product has to be positive? Positive times positive is positive, right? Where they're both negative, what's the sign going to be of the product? Positive, yeah. It's only where they're opposite in signs, where I have an odd number of negative factors, that I'm going to get negative. And isn't that consistent with what we said? Right? Didn't we say before that the result of all this was going to be when x is greater than 2 or less than negative 2? Well, there it is. right? That's when this function is positive valued. If that's what we're asking is where is it positive valued, it's going to be there and there, right? What if we wanted to know where it's less than 0? Right there, right? Where it's negative valued, where the product is negative valued. Negative valued means less than 0. That's kind of cool, isn't it? Yeah.
So were we to not already know the answer to the question, how could we use that to extrapolate the answer?
Well, that gave us the same answer, didn't it? If we look back at what we did, look back, boy, it's been a long time ago, back here, right? We said that if we solve this, x squared minus 4 is greater than 0. We solved it, right? And we got the answer, either x is less than negative 2 or greater than 2. Where is x squared minus 4 greater than 0? Right there and right there. So it doesn't it actually gives you the answer. Okay? Make sense? Where we did a bunch of work back here and we saw that we wanted to know where is x squared minus 4 less than 0. We did a bunch of work and we found it's less than 0 between negative 2 and positive 2. The product is less than 0 when the product is negative, so there it is, right, between the two. Okay, good. All right, questions? Okay, there's a lot of review stuff built in there, but this is all pretty good stuff. Okay, so what about something, how much time we got, 6 minutes?
Yeah.
Okay, good, that's all I need. Okay, so let's look at a couple more of these here, and then we'll pick this up tomorrow where we leave off. But this, I want to at least get through a couple examples of this. So what is this? Let's do the top limit. What's the limit as x approaches 1? What's that mean?
It's not a true limit.
Doesn't exist. Right? There's no limit. What about the bottom one? Oh, hang on, bottom one, I want to do this. Now I want to go. Something like that. Okay? So what's that give us? 3 over what? Yeah, now think about this. If I subtract, what does 1 plus mean? 1.00, right? It means something slightly bigger than 1. How big? How much bigger than 1? It's arbitrary, but bigger than 1, right? If I subtract a number that's bigger than 1 from 1, what's the result? Okay, a small negative. How do you think I might represent that? 0 minus, yeah. What does 0 minus mean? 0 minus means a vanishingly small negative number. How do we interpret this? There's 2 parts to our answer then. So the fact that we're dividing a non-zero number by 0 means it's infinite, right? It explodes. So that part right there, this part of the recipe, the 3 divided by 0 gives us infinity. But now we got to pay attention to the signs. If I divide a positive by a negative, what's the result? So the answer is negative infinity.
So is that what you're gonna want in middle now?
Say it again.
Is that what we're going to be putting in middle now?
Yeah, if it yeah.
Okay.
Yeah, if I ask for, we do what we call an infinite limit. What if we were to do the same thing? Let's take the same limit from the left.
Positive.
Yeah, we're going to get 3 over, now we're subtracting something less than 1 from 1, and so we're going to get a slightly positive leftover, right? Dividing by 0 gives us infinity, positive over positive makes it positive. Well, that tells us something pretty cool. That tells us we actually have kind of a sketch here. With just that limited information, we could do a pretty quick, accurate sketch of this. Where's the asymptote going to be?
X equals 0.
No, at 1, because 1 gives us a 0 of the bottom but not the top. So that tells us right away that at 1, we're getting an asymptote. As we approach from the right, it's diving down, right? As we approach from the left, we could even say, well, the horizontal asymptote's at 3 for reasons you don't know yet, but you will soon. So it looks like that from the right and it looks like that from the left, and that's what that function looks like. Just with that little bit of information, right? Okay, how about something like that? Okay, 0 plus over 3 is unnecessary. This is a trick one. Don't make this harder than it is. What's the answer? 0. Does the plus part of that even matter? No. I'm getting on the top. In this case, on the top, it's irrelevant in this case what sign the top is. I mean, we can call it if you want to. We'll just put it up there for now, but I'm going to get 0 plus. Big deal. Who cares? I'm going to get 0 over, what, 3?
Yeah.
What's 0 over 3? 0. It approaches 0. Do we care what the sign is? No, it's approaching 0. It's a finite amount. Right? We're getting a finite answer. That 3 plus doesn't help us a bit. How's that different than over here? Well, big difference. Positive infinity and negative infinity are pretty different, right? Infinitely different, right? Over here, if we wanted to be very particular about this and say, okay, well, I'm going to get 0 and it's positive 0. Who cares? It's just 0. What's the difference between 0 plus and 0 minus? The limit is 0. See the point? Unnecessary information, extraneous. Okay, what about that one, though? We're going to run out of time, but here I'm going to get something over 0, aren't I?
Yeah.
Right? So what's that tell us? If we get, it's not 0 over 0. If I get a number over 0, we used to call that DNE, right? Now we can do better, though, and that's what we'll leave off for tomorrow. Now we want to be able to say, we're not just going to leave this as no limit. We want to be able to write this as plus or minus infinity. Which one is it?